Good morning, students. Our today's topic is inverse of a linear operator. So firstly, let us define 1 linear operator. A linear operator T from domain of T into Y. Domain of T here we have denoted by dt. So the linear operator defined on dt into Y is said to be 1 or injective if we take two elements x1 and x2 from the domain of T such that the elements are different. Then this should implies that the images are also different. T x1 denotes the image of x1 under T and T x2 denotes the image of x2 under T. So different elements have different images. Then we say that the linear operator T, that is 1. Or we can say that if the images of the two elements under the linear operator T are same, then this should implies that the elements are also same. So we can say that T is 1 if T x1 is equal to T x2 implies that x1 is same as x2. So in this case, if the mapping T is injective or 1, in that case there is a mapping denoted by T inverse, and this is defined from RT means range of T to the domain of T, and defined by T inverse of y naught is equal to x naught, where this y naught is the image of x naught under T. This mapping is called inverse of T, and by definition T inverse T inverse T will become identity. So that identity of x, that will be x for every x belonging to the domain of T, and also T inverse of y, where y belongs to range of T, that will also be y, because T inverse will become identity and identity of y, that will be y. Now next there is a theorem. Let x and y are two vector spaces, both real or both complex, and let T from dt into y be a linear operator with a domain of T contained in x and range contained in y. Then we are to prove that the inverse from RT to dt that exists if and only if image of x is equal to 0 implies that x is equal to 0, where x belongs to the domain of T. In the second part, we will prove that if T inverse exists, then that is a linear operator. And in the third part, we prove that if dimension of domain of T is n, which is finite, and T inverse exists, then the dimension of range of T is same as dimension of domain of T. So first of all, we prove the first part. In the first part, we are to prove that if T inverse exists, then Tx is equal to 0 implies x is equal to 0. Here x belongs to the domain of T. So let us take x belongs to domain of T and image of x under T is equal to 0. We are to prove that x is also 0. Now because we are given that inverse of T exists, therefore we can apply T inverse on both sides of this equation. So applying T inverse here, this will become T inverse of Tx, and here T inverse of 0, that will be 0, and T inverse T is identity operated on x, that will be x. So we get x is equal to 0. This proves the first part. Now conversely, let us take for x belonging to domain of T, Tx is equal to 0 implies that x is equal to 0, and we are to prove that the inverse of T exists. Now inverse of a linear operator exists if and only if it is 1 1. It means in order to prove that T inverse exists, we have to prove that T is 1 1 linear operator. In order to prove 1 1, let us take two elements x and y belonging to domain of T such that their images under T are same. So let us take image of x under T is equal to image of y under T. We have to prove that these two elements x and y are same. Now Tx is equal to Ty. So from here we get Tx minus Ty is equal to 0. Now because T is linear operator, so Tx minus Ty can be written as image of x minus y under T. So we get image of x minus y under T is equal to 0. Now we are given in the condition that for x belonging to domain Tx is equal to 0 implies that x is equal to 0. Now here, because x and y belongs to domain of T and domain of T is a vector space that is closed under vectors addition, so we can say that x minus y is an element of domain of T, and therefore if its image under T is 0, then by using this condition the element x minus y, that is also 0. So we get x is equal to y. So this proves that T is 1 1 and therefore T inverse exists. In the second part, we are given that inverse of T exists and we are to prove that it is a linear operator. So in order to prove this is linear operator, let us take two elements x and y belonging to the domain of T. Now by definition of T, because T is linear operator from dt into RT, so images of x under T and image of y under T, these are the elements of range of T. Now let us prove the first condition for linear operator. So let us take two elements Tx and Ty from RT and we have to prove that T inverse of Tx plus Ty is equal to T inverse of Tx plus T inverse of Ty. Now because T is linear operator, so Tx plus Ty can be written as image of x plus y under T. Now this can further be written as T inverse T operated on x plus y. T inverse T is identity, so this will become identity of x plus y, that will be x plus y. Substituting the values, now x can be written as T inverse Tx and y can be written as T inverse Ty. So this proves the first condition for linear operator. In the second condition, let us take a scalar alpha and an element Tx from the range of T. Now let us find T inverse of alpha Tx. Now because T is linear operator, so alpha Tx can be written as T of alpha x. Now T inverse T, that is again identity, so identity of alpha x, that will be alpha x. So we get T inverse of alpha Tx is equal to alpha into T inverse of Tx. So this proves that T inverse is a linear operator. Now in the third part, we are given that the dimension of domain of T, that is n, which is finite, and T inverse exists. We have to prove that the dimension of range of T is same as the dimension of domain of T. Now we discussed in the previous theorem that for a linear operator T from domain of T into RT, if the dimension of dt is n and that is finite, then the dimension of range of T, that is also less than or equal to n. So using that result here, we get dimension of RT is less than or equal to n. Now n is dimension of dt, so we can put the value of n here. So we get dimension of RT is less than or equal to dimension of dt. Now T inverse exists. It is given to us, and T inverse is also a linear operator, so we can use the same result again. So we get dimension of dt is less than or equal to dimension of RT. Now we can combine these two. So we get from here dimension of RT is equal to dimension of dt, and this completes the proof of the theorem.